me okay. All right. Okay, so let me just move a window really quick. Okay. All right, so we will start with L'Hopital's rule, which I'm sorry that this is rehashing a little bit what we discussed earlier, but I think it's for the best. So, okay. So what is L'Hopital's rule? We want to evaluate a limit of the form, this, where we have a ratio of two functions, and we're in a situation where the top and the bottom of this fraction are not well defined at a. So here we could be in the situation where f of a is 0 and g of a is 0. So then if I actually tried to evaluate this at a, then I would get 0 over 0, which is undefined. So my usual method of just evaluating the limit at the values of the functions doesn't really work. But also since one of the numbers is 0, or since both of the numbers are 0, it's not like I would expect this limit to necessarily be infinity, so to necessarily be not well defined. So okay, so L'Hopital's rule tells you a way of evaluating this limit in these kinds of situations, right? So this is a simplified version of L'Hopital's rule. Okay, and what does it say? So it says if I have two functions f and g that satisfy this first condition, so f of a is 0 and g of a is 0, and I suppose that the derivatives are finite and non-zero, then okay, then the limit of the ratio f of x over g of x as x goes to a, that's this term, is equal to the limit of their derivatives as x goes to a, limit of the ratio of the derivatives. And that's just equal to, so under the hypotheses that f prime of a and g prime of a are well defined, this is just the ratio of these two things. Okay, and this is the example I was doing. So that was a quick recap of what we did before, what we did at 2. And I really quickly, okay, so the example I did was just messed up, so I'm going to redo it. So this is, I changed things from the example before. So here we want to use L'Hopital's rule to evaluate the limit of e to the x minus 1 over 2x as x goes to 0. So I changed some of the limiting stuff a little bit to make L'Hopital's rule actually apply. Okay, so here, okay, so in this situation, so we have f of x is equal to this, g of x is equal to this, okay, and we see that f of x goes to 0 as x goes to 0, and also g of x goes to 0 as x goes to 0. So this is a totally situation where L'Hopital's rule applies. So we can calculate the derivatives of the two functions. So in this case, we get the derivative of the top function f is e to the x, derivative of the bottom function is 2. And so by L'Hopital's rule, we have that this limit is given by e to the x over 2, which is, the limit is x goes to 0 of e to the x over 2, which in this case is 1/2. So before I had something different written down. Maybe I'll say a little bit about that previous example just to explain the wrongness of it. So okay, so yeah, so if I took the limit, if I changed this and instead asked for the limit as x goes to 0 of e to the x minus 1 divided by 2x minus 2, or maybe, yeah, I think this is more similar to the example I asked about last time. So here, this is a situation where L'Hopital's rule would not apply. So if I change this to 2x minus 2, then L'Hopital's rule would not apply. Doesn't apply. And the reason is because the bottom function as x goes to 0 doesn't limit to 0. It limits to something finite. So in this case, you can see that the limit is just, the top thing limits to 0 and the bottom thing limits to -2. So here the limit is just 0. And you can see that in this case, L'Hopital's rule actually explicitly fails, because if I compute the derivatives of both of them, and I take the limit as x goes to 0 for that, then the result is 1/2, which is not 0. Yeah, so it's pretty easy to see there that the yeah, that this is a situation where L'Hopital's rule fails. Okay, so hold on, give me a moment. Okay, yeah, all right. So all right, so now, okay, so there's a more general version of L'Hopital's rule, which is what I was going into when the which is now we're kind of at the part where we left off last, like at 2, or at the 2 for the 2 o'clock section. So, okay, so there's a more general version of L'Hopital's rule. Let me adjust something really quick. Okay, so there is a more general version of L'Hopital's rule that someone's mic is on. Do you think if your mic is on, do you think you could turn it off unless you want to say something? Thanks. Cool. Okay, so all right, thank you. Anyway, so okay, general version of L'Hopital's rule. Let's say that f of x and g of x satisfy one of the following two conditions. So here either okay, so there's two possible circumstances where you could want to apply L'Hopital. So the first one is where the limit of f of x and is 0 and the limit of g of x is 0. This is basically the first case, although technically speaking, the function doesn't actually have to be defined at 0. So you could have a really weird, you could have some really weird function that has a limit at 0 but isn't actually defined there. Okay, so this is the first possibility, and the second possibility is that you have the limit of f of x is instead of being 0 is plus or minus infinity as x goes to a. And then similarly for g. So the limit is x goes to a of g is plus or minus infinity. Then in that situation, you also have, so, you know, this more general version of L'Hopital's rule says that in that situation, you have two possibilities for the limit. So first of all, if the limit of the ratio of the derivatives exists, so basically the limit is some constant c, that constant can be 0, it can be, you know, any number as long as it's not plus or minus infinity. Then the limit as x goes to a is also c. So basically, when the limit of the ratio of the derivatives exists, then so does the regular limit, or the limit of just the original functions, the ratio of the original functions, and that limit agrees with the limit of the ratio of the derivatives, right? So this part A is basically saying exactly the same thing as the first L'Hopital's rule, except now I can use it when f and g go to plus or minus infinity. Okay, and then the second one tells you that if the second possibility tells you that if the ratio of the derivatives, so f prime over g prime, f prime of x over g prime of x goes to plus or minus infinity as x goes to a, then the limit of f of x over g of x also does that. So it also diverges to plus or minus infinity. So basically, this gives you, this is a much more general version, but you know, for most purposes, you'll basically be asked to use this regular version of L'Hopital's rule. But the more general version will show up sometimes in questions. So it's good to know both of them. I think it's good to try to wrap your head around the simple one first, and then to try to think about what the general one is saying. Okay, so I'll do my second example now. Hopefully I didn't mess this example up like I messed up the first one. Okay, so here I'm taking the following limit. So suppose I am taking the limit of e to the x minus 1 divided by 2x minus 2, right? And I'm taking the limit as x goes to infinity. So, okay, so by L'Hopital's rule, okay, I know that e to the x minus 1 and 2x minus 2 both go to infinity as x goes to infinity. So, you know, the limit of the top guy is infinity, this is infinity in the limit. And then the bottom guy is also infinity in the limit. But I kind of know that the exponential function e to the x grows faster than the function 2x minus 2. So 2x minus 2 sort of grows linearly, so it's really slow, and then e to the x grows really quickly. So what I expect this limit to be is the top part of the limit should overpower the bottom part of the limit, and I should get infinity. And that's exactly what L'Hopital says. So I'm allowed to apply L'Hopital to this situation because the both top and the bottom functions both limit to infinity. So when I look at what happens in that limit, I take e to the x minus 1 divided by 2x minus 2, and I look at the limit as x goes to infinity of e to the x over 2. And that, this is what L'Hopital tells me, that this limit on the left is equal to this middle limit. And then that limit I can clearly see as infinity. That definitely diverges. So in particular, this limit on the far left doesn't exist. It diverges, and the limit, it actually diverges to positive infinity. So that's what I can take away from L'Hopital. Okay, and then the second example is similar. So here I have ln of x squared over x, and I want to know what the limit of this thing is as x goes to infinity. And here, again, both of these functions diverge to, ln of x squared goes to infinity as x goes to infinity, and so does x. So they satisfy this second version of L'Hopital, the second criterion for L'Hopital. Okay, so now I want to know. So using L'Hopital, I take this limit, and according to L'Hopital, I can rewrite it as this limit. So the limit of 2 ln of x divided by x over 1. And that's just me taking the derivative of the bottom and the derivative of the top. And for the derivative of the top, I'm using just the regular chain rule. So, or I guess product rule. Okay, well, I guess you can look at it either way. All right, so I apply product rule, and I get the top guy that is that, and the bottom guy is that. And now if I just rearrange this a little bit, I get 2 ln of x over x. And now what you'll notice is that I'm again in a situation where where both the top and the bottom diverge. So here, the top part is now ln of x, or 2 ln of x, not ln of x squared, but that still goes to infinity as x goes to infinity. And the bottom term is x, and that the limit of that as x goes to infinity is also infinity. So here, in order to apply L'Hopital, we actually have to do it again, right? We have to apply L'Hopital a second time. So if I apply L'Hopital a second time, I see that this limit, 2 ln of x over x, is equal to, okay, I take the derivative of the top guy, that's 2 over x, and I take the derivative of the bottom guy, that's x, that's 1, right? And now I see that this guy is equal to just 2 over x. So the limit of that as x goes to infinity is 0. And so that actually gives me some well-defined limit. So here, an important thing to note is that sometimes when you're asked to evaluate a limit using L'Hopital, you have to apply L'Hopital 2 times. So you have to do one application of L'Hopital to get one limit, and then an additional application to get the limit of that limit, or something better for that limit. And you might have to do it 3 or 4 times. Probably we won't ask you to actually do that, but in principle, you could have to do it a lot of times in order to get to something that actually has a limit. Yeah. Okay, so anyway, that was some reasonably sophisticated examples. So does anyone have any questions about, I don't know, L'Hopital's rule, the simple one or the complicated one, or either of the examples I did? Questions? You can unmute yourself if you want. I was just asking you guys to do it for noise purposes. Okay. All right, so if there are no questions, I will ask you guys to give these exercises a shot. So yeah, so please evaluate each of these limits using L'Hopital. They're all of the x goes to 0 variety, so relatively simple ones. Okay, and I'll give you guys until let's see, what's a good amount of time? I'll give you guys like 15 minutes to do these, so I'll give you until 4:10, and then I'll go over the solutions. Okay, and of course, if you have any questions, please message me on the chat, or you can just speak up. It's up to you. All right, I'm going to stop you guys a little early because I think, um, oh, hold on. Okay. All right, so I'm going to stop you guys a little early and get started with the answers. All right, so first, let's start with the first one. All right, so I want to find the limit as x goes to 0 of x e to the x over 2 e to the negative x minus 2. Okay, so I see that x times e to the x goes to 0 as x goes to 0, and e to the 2 minus x, e to 2 times e to the negative x minus 2 also goes to 0. Okay, and so now I can take the derivative of both of, so because of this, I want to apply L'Hopital. So I take the derivative of the top and the bottom. So if I take the derivative of the top, I get this. Sorry, that should be plus. Okay, and then I get a plus e to the x, and then that should be a minus because there's a minus there. And then I get an e to the negative x, and then on the bottom I get a negative 2 e to the negative x. Okay, and I want to take the limit of that. Got to make a little room there. Now I want to take the limit of this as x goes to 0. Okay, and here now I see that, okay, this part goes away when I take the limit, and then this e to the negative x, really now both the top and the bottom are now well defined at 0, so I can just plug in 0, and I get e to the 0, negative 0, I guess, divided by negative 2 e to the negative 0, which is just another 1/2 or negative 1/2. Okay, so that's how you answer A. Okay, and then the next one, so for the next one, we'll do, okay, for the next one now, we're going to check, remember, the first step of what we do is we have to check that L'Hopital is actually, necessary or applicable in this situation. So if I look at the thing that I'm taking the limit of, okay, so if I look at the thing I'm taking the limit of, well, the bottom thing definitely goes to 0. This bottom guy definitely goes to 0 as x goes to 0, right? But the top guy, as x goes to 0, goes to ln of 2. Okay, so so ln of e to the x plus 1 goes to ln of 2, which is not 0, as x goes to 0, while the bottom thing, 2 e to the negative x minus 2, goes to 0, just like in the previous problem. So this guy goes to 0. And so now the top part, so basically this means that this actually diverges. So the limit, so here, yeah, I'll just say before that, yeah, so this says that L'Hopital does not apply because in order for L'Hopital to work, either both the top and the bottom have to go to 0, or the top and the bottom have to go to infinity. I can't, if one of them goes to a finite number, like ln of 2, then L'Hopital doesn't apply. So I cannot apply L'Hopital here. And instead, I just think about what the limit should actually be. So if the bottom goes to 0, but the top goes to some finite thing, then that means that this whole thing diverges because the bottom part will go to 0, and that means 1 over the bottom thing will go to infinity. And so the limit will go to infinity, will go to some infinity. And then if you think carefully about the sign of the bottom, so the thing on the bottom goes to 0, and it goes to 0 from the left, meaning that when x is close to 0 and positive, then this is very negative. This is small and negative. Yeah. So the limit. So basically, if x is coming to 0 from the right, which means it's coming from x is positive, and it's going to 0, then this limit will then the top thing will be ln of 2, and the bottom thing will be a very small negative number. So the limit will be negative infinity. But I guess since they don't say whether or not x is positive or negative in this limit, so meaning whether or not you're approaching x equals 0 from the left or the right, the best we can do here is just say that this diverges. Although if I put like x is coming to 0 from the right, which would be like, I think something like this, so x plus to 0, meaning it's coming from the right, then this thing would diverge and go to negative infinity. And if I said it was coming from the left, then it would go to positive infinity. Anyway, I think the full answer in this case would just be that this thing diverges. So maybe we'll just leave it at that. Okay. And the last thing we want to set, so now we want to check the last one. So here we want to find the limit as x goes to 0. That's terrible handwriting. Limit as x goes to 0 of this set of ratios. So this is like e to the x divided by x squared minus 1 over, what does it say? Minus 1 over x squared minus 1 over x. Okay, and we want to know what happens to this as x goes to 0. So here we have to combine the fractions in order to directly apply L'Hopital, right? Because L'Hopital doesn't say anything, you know. So if I look at this part, if I look at this left part of the fraction, that guy goes to infinity as x goes to 0, and so does 1 over x squared. So I can't like directly apply L'Hopital here because you know, none of these individual fractions satisfies the L'Hopital condition. But if I combine the fractions, I see that this is equal to e to the x minus 1. So I can rewrite this as e to the x over x squared minus 1 over x squared minus x over x squared, just by multiplying the last term by 1 over x, or by, I guess, x over x. And then I can combine the fractions to be e to the x minus 1 minus x divided by x squared, right? So that means that it's sufficient to compute the limit of this guy. So if I write that down, so if I look, so now is the time when I can apply L'Hopital. So if I take the limit as x goes to 0 of e to the x minus 1 minus x divided by x squared, well, according to L'Hopital, this is equal to the limit as x goes to 0 of e to the x minus 1 divided by 2x. That's just me differentiating the top and the bottom once. Okay? And then this guy still has the top and the bottom going to 0 as x goes to 0. So I have to apply L'Hopital again. So now I apply L'Hopital again, and I get e to the x divided by 2. And so the limit is 1/2. So a lot of the examples, they've ended up being 1/2 this time. That wasn't on purpose. That just is what happens. Okay, anyway, so that's the answer. So what I do is I combine the fraction into one single fraction, and then I apply L'Hopital twice to get the actual answer. All right, does anyone have any questions or notice that I made a mistake in any of these calculations? Questions, errors? No? Okay. All right, so if you have anything to say, definitely just speak up or talk to me in the chat. Otherwise, I will keep going. All right, so the next thing we want to talk about is indefinite integrals, and this box is a little bit misaligned, so I'm going to fix that. Okay. Okay, so the next topic that we're talking about is indefinite integrals. All right, so indefinite, maybe I'll use the highlighter. So an indefinite integral are integrals where the bounds of integration are infinite. So that means that they're integrals where the a and the b that you're integrating from and to can both be infinity, right? So okay, so here's the actual definition. So suppose I have a function f of x with antiderivative big F, right? So that means that the integral of f up to some shifting constant, the big integral of little f is big F, right? Okay, then we can define the integrals. We can define the integral from a to infinity of f of x dx. We can define this to be the limit as b goes to infinity of integral from a to b of f of x of dx, f of x dx. Or equivalently, if I just evaluate this integral in the middle, this definite integral, I get I can write the middle thing equivalently as the limit as b goes to infinity of big F of b minus big F of a, where big F is some antiderivative of little f, right? So it's possible. All right, so all that means is that in order to take an integral to, from a to infinity, all I need to do is take an integral from a to b for some finite b, and then I find some formula for that integral in terms of b, and then I evaluate what that formula does as b goes to infinity. Okay, so if the limit, so there's, you know, it's not true that these indefinite integrals always exist. So if the limit on the left, whoop, I'm moving the box. Don't want to do that. Stop moving box. Sorry, guys. Okay, so if this limit exists, or you know, any of the limits that I'm using to define this, if any of these limits exist, then I say that the integral converges, and otherwise I say the integral diverges. All right, so that's just terminology for what it means to converge and diverge if I'm integrating over some infinite thing. And then I define the indefinite integrals written like this in the analogous way. So basically, if I was looking at the integral from negative infinity to b, I would take, instead of taking the limit of big F of b minus big F of a as b goes to infinity, I would take the limit as a goes to negative infinity. So I would take the other part of the integral, the other part of this expression, to go to negative infinity. And then similarly, if I was looking at an indefinite interval where both of the bounds are infinite, then I just take the limit as both a and b go to you know, where b goes to infinity and a goes to negative infinity. So so I can define these integrals where I replace any of the bounds of integration with infinity or negative infinity. And I just have to be careful to make sure that that integral actually exists. All right, so let's do some examples. All right, so an example of the kind of question here would be find the integral from 2 to infinity of 1 over x squared, and find the integral from negative infinity to 0 of e to the x. Okay, so these are two different indefinite integrals. All right, so for the first one, I could give you, okay, so for the first one, okay, I'm just going to use the definition of indefinite integral that I just gave you. So the integral from 2 to infinity of 1 over x squared, that's what the first thing I'm asked to get, is just the limit as b goes to infinity of from 2 to b of the integral from 2 to b of 1 over x squared, right? So I know how to integrate. I know how to take this inner integral, right? So this integral where from 2 to b, where b is some finite number, is pretty easy. That's just negative 1 over b, which is the, you know, so I know that integral of 1 over x squared is negative 1 over x plus c, right? So if I look at this inner integral, this box thing, I can just write that as negative 1 over b minus 1 over 2. So the negative 1 over 2 comes from this bottom limit. All right, and then now if I evaluate this, maybe I'll write in a little more to this, a few more steps here. So I can write this as 1/2. So I can write this as 1/2 minus 1 over b. Sorry, this is a little cumbersome to do. So I can write this as 1/2 minus 1 over b, and I just want to take the limit of that thing as sorry, and this is not the most fun to navigate this. Okay, so I just want to take the limit of that thing as malfunctioning OneNote. Technology is not liking me today. All right, okay, anyway, so I just want to take, so if I look at this limit, negative 1 over b minus negative 1 over 2, that's just equal to limit as b goes to infinity of 1 over 2 minus 1 over b. And minus 1 over b definitely goes to 0 as b goes to infinity, because obviously that just gets extremely small. And the 1/2 stays the same. So the limit of that whole thing is just going to be 1/2, which I'm going to copy now. Okay. Why do you hate me, computer? All right, well, anyway, the limit, let me just write it. Okay, so the limit of that is just 1 over 2. Okay, man, I really got to get my technology under control here. Anyway, okay, so that limit, this integral, the point is this indefinite integral is 1/2. All right, and all I did there was I just plugged in the definitions and evaluated the right limit. All right, so the next thing is let's say now I'm doing the next part of the example. So suppose I wanted to evaluate the integral from negative infinity to 0 of e to the x. So I want to evaluate that. Then that's just by definition, the limit as b goes to negative infinity of, the integral from b to 0 of e to the x. Now I can write that as the limit of 1. So now if I evaluate the integral, so the integral of e to the x is just e to the x plus a constant. So if I evaluate this definite integral from b to 0 of e to the x, I get 1 minus e to the b. And now if I take the limit of that as b goes to infinity, as b goes to negative infinity, it's very important, then that limit, the e to the b part goes away, because the limit of e to the b as b goes to negative infinity is 0. So the whole limit of that whole thing is just going to be 1. Okay. So let's see if anyone has any questions in the chat real quick. Doesn't look like it. All right. So does anyone have any questions about indefinite integrals, how this is supposed to work? Sorry, the notes are kind of a mess. Not having a great time with my computer today. Okay, I'm just gonna stop trying to do this. All right. So does anyone have any questions about this stuff? Yay, nay? All right, sounds like no. So I'll let you guys give these exercises a shot. All right, so those are the two exercises. So just try to do those indefinite integrals, and really it should just be a matter of, writing down the limit and then computing the kind of normal integral that you would compute. Okay, so I'll give you guys like 10 minutes to do this. So we will reconvene at 4:33, and definitely ask me, or 4:33, and yeah, definitely ask me questions if you need any help. All right. I'm going to change the second one exercise in this a little bit because I think that this is a good example of a situation where, so the second integral is a good example of a situation where these things aren't well defined. So maybe I'll talk about that a little bit. But let me just make this one a little simpler by squaring the bottom. So, I'm changing the bottom integral slightly. And let me just do that really quick. Oop, that's not what I want to see. What are you doing, computer? Okay, just wait for me for like a minute to fix this. Oop. All right. So okay, so I fixed the integral. So please try that one. That one's I think, a little more straightforward than the one I posted, than the one I put before. Okay. All right, you know what? Hold on. Okay, I just suck at this, so don't even try this one. Just ignore it. Okay, I'm gonna highlight. I'm gonna write that on the thing. Okay, I'll try to come up with a better one to put in the notes online, but just don't try this one. I'll explain a little bit of what makes that one so weird in a second, but otherwise, just ignore it, and I'll let you guys have a little bit longer for the first one. So we'll talk about the first one at 4:33. All right. Okay, so I will, okay, so let's start with this one, the one I didn't mess up, and then we'll talk about this highlighted one in a second. Okay, so first of all, okay, the first one's pretty straightforward, so I'm just integrating this. Okay. And so by definition, I just apply, okay, so I just apply the definition for this indefinite integral, and that's given as the, let me draw that infinity again. All right, so that's given as the limit as b goes to infinity of the integral from 2 to b of 3 over x cubed, which I'll rewrite as, I'll rewrite 3 over x cubed as something a little better. So 3x to the negative 3 dx, okay. So if I integrate, so I know that how to integrate 3 times x to the negative 3. That's just given as, you know, negative 3 over 2 x to the negative 2, right? So that's the integral of that inner part. And then I just have to evaluate this as the bound, so that's 2 and b. Okay, so that gives me, so if I look at that, that's the limit as, also this should be b, sorry. Okay, so that if I take this evaluated integral and look at the limit, I get limit as b goes to infinity of negative 3 over 2 times b to the negative 2 minus 2 to the negative 2. Okay, and b to the negative 2 as b goes to infinity goes to 0, because as b goes to infinity, b to the negative 2 is 1 over b squared, so that's going to go to 0 as b goes to infinity. And so this whole, when I take the limit, that cancels out, and I get, you know, if I multiply negative 3 over 2 times negative 2 to the negative 2, then all of that comes together and I get 3 over, I believe I get 3 over 8. And that's the answer. Okay, and for this first, for the one that I highlighted and told you not to do, so the reason why this one is kind of annoying is because, so let me say something a little bit about why this is annoying. So, okay, so if I look at this integral, 2x divided by 1 plus x squared dx, right? So if I write this out, so the actual way that you're supposed to evaluate a limit like this is you take the limit as b goes to infinity and a goes to negative infinity of the integral from a to b of this, right? Which I can write, so I can write that as, so I have to take 2 limits in order to evaluate that particular integral. And okay, so the thing about the inner part, the important thing about the inner part here, and the reason why I've made the first change is because this guy, so if I look at the inner, hold on, I gotta move a window really quick. All right, so if I look at the inner part, if I look at this, so if I look at 2x divided by 1 plus x squared, this is just, so squared, this is just equal to, you know, I can write this as negative 1, the derivative of negative 1 plus x squared or sorry, to the negative 1. So I could prime. Okay, sorry. So this thing is the derivative of, like, this whole thing is the derivative of negative 1 plus x squared to the negative 1. You can check that by just taking the derivative using chain rule. Okay, so if I was just naively doing this, I could write this as 1 plus x squared to the negative 1 evaluated from a to b, and then I just want to take the limit of that as a goes to infinity, negative infinity, and b goes to infinity. But the problem is that what you end up getting from that calculation actually depends on, like, basically what you get is that limit. It's basically, it's a little tricky to think about what you actually get on this, on that limit. So if you actually take b goes to infinity and a goes to infinity, then the result is 0. So technically, I guess this thing would be 0. But I think if you take the integral on, yeah, you know what? Let's just stop. Let's just stop it there. So basically, this ends up being 0 if you take both of these limits. But I think it's a little bit weird to think about that. And the reason that's happening is because, you know, if you graph this thing, then you'll see that, like, the graph kind of looks like this. where you have two mirror sides, both of which have finite non-zero integrals, where the resulting integrals on either side cancel out. Anyway, so I guess maybe this one was a little less weird than I thought, but the answer for this final highlighted integral is the integral of 0. And the way that you do that is you just do the regular integration thing, and then you take the limit as b goes to infinity and a goes to infinity, and you'll see that as b goes to infinity, so as b goes to infinity, and you look at 1 plus b squared to the negative 1, that thing will go to 0, and then similarly as a goes to negative infinity. So anyway, so the limit of this is 0 is the point, but it ends up being a little bit complicated. I probably should have just told you guys to go through with it. It didn't end up being so bad. Okay. Anyway, so sorry that example was a little more complicated than I wanted it to be. Does anyone have any questions about indefinite integrals or about these two examples that I asked you guys to try? Okay. I hear nothing. All right. So there's one more topic that we'll do today, which I'm just going to talk about that topic and then give an example, and then we'll finish. So, okay. So what is that topic? So the topic I have in mind is called Newton's method, and I'm going to probably unwisely try to rearrange things a little bit here. Give me a moment just to move things around. OneNote sucks, man. This is like not great. Not great. Okay. Anyway, so all right. So Newton's method. All right. So what is Newton's method? So this is like extra credit. This is like the extra credit material for the people who want to take the class for a grade. So you don't necessarily need to listen. But if you're taking this for a grade, then you probably want to tune in. Okay. So Newton's method is a method for finding approximate solutions. So Newton's method is a method for finding approximate solutions to the formula f of x equals 0 for a in some range from a to b. Okay, so you might want to find a solution to something like this, f of x equals 0 for x in some range. But you might have a situation where that equation is very difficult to solve explicitly. So in that case, you can find an approximate solution by utilizing Newton's method. And basically the way that Newton's method works is you kind of inductively, step by step construct a closer and closer approximation to the solution by constructing the sequence basically procedurally. So it's a lot like Euler's method. So okay, so what actually happens? So let's say I have a function f, and let's say I have a sequence so what Newton's method starts with this result, which says that if I have a function f of x and I have a sequence Cn that satisfies this property that Cn is equal to Cn minus 1 minus f of Cn divided by f prime of Cn. So basically I can get the next element of the sequence from the one previous to it by adding this should be n minus 1. By adding by subtracting the value of f at Cn minus 1 divided by the derivative of f at Cn minus 1. Okay, and here we're assuming that this fraction is well defined. So that means that f prime of Cn is non-zero for each n, and that Cn has a limit. Okay, in this situation, the limit of the sequence is a 0 of f, and in particular, the sequence approximates a 0 of f. So that means that as n gets larger, it will converge to a 0 of f. And in particular, so as n gets larger, this sequence is going to approximate a 0 of f. So you can use this. You can basically use this definition or use this fact to procedurally generate approximate solutions to the equation f of x equals 0. Okay. Anyway, so that's pretty sketchy. So maybe I will. So we're going to end with an extended little example of what Newton's method looks like in practice. Okay, and so in practice, the way that you use this fact, so this thing that I'm calling Newton's method, is you actually compute this. You compute a sequence like this. You basically start with some fixed number, and then you create a sequence like this. So you compute C1, C0, C1, C2, etc. And then you stop at some finite C5 or something like that, and you use that as your approximation. So okay, so here's the example where I kind of carry that out. All right, so suppose I wanted, so here's the application. So suppose I want a solution, an approximate solution to the equation 3x cubed minus x squared plus 5x minus 12 equals 0, right? So I want to solve this particular equation where f of x is this polynomial that I wrote, that I underlined there. Okay, and I want to do this with 4 steps of Newton's method. All right, so what I do is, first I calculate the derivative. So the derivative of f is 9x squared minus 2x plus 5. And now I just, compute approximations. Yeah, so I compute like a sequence of these CIs. So I'm going to make a sequence which satisfies these properties that I talked about in this boxed Newton's method definition there. All right, so first of all, I'll start by declaring, the first element of my sequence, C1 is equal to 1, right? Then I want to just calculate each net, the next elements of the sequence. So C2 is equal to C1 minus f of C1 divided by f prime of C1. So if I compute those numbers, well, C1 is 1, and then f prime of 1 is, so I think f prime of 1 ends up being like, we can actually check. Yeah, so f prime of 1 is 12, and f of 1 ends up being -5. So if I plug f of 1 and f prime of 1 into this formula, I get 1 minus -5/12, which ends up being this. And I scribbled it out. That shouldn't be there. Okay, so that's my C1. So now I basically use this formula from Newton's method to compute the next step, right? Now I do it again. So I say, okay, C2 is equal, C3 is given by C2 minus f of C2 divided by f prime of C2. I know what C2 is, so C2 is that. So now I just plug C2 into this formula along with f of C2 and f prime of C2, which I can compute very easily by plugging in 1.4167 into f prime and f, okay? And that spits out, when I compute this, it spits this number out. All right, so that's another step of Newton's method. And then now I do one more step. So now I have FC4 is equal to C3 minus f of C3 divided by f prime of C3. And that difference I can compute using C3 and the formula for f and f prime, and that gives me 1.33333, whatever. And one thing you'll notice here is that these numbers are getting progressively closer. So 1 went to 1.4167, then 1.467 went to 1.3373, which is closer to the, so C3 is closer to C2 than C2 is to C1. And then when I go from C3 to C4, it changes like very little, right? So when I go from C3 to C4, only like, the 7 changes to a 3, but other than that, they're like basically the same number. And so as I take higher and higher CKs, the numbers get closer and closer. And this is, so this is the 4th step that I would get. And that would be the thing I box as my answer. So anyway, the procedure for doing, maybe I'll write this out explicitly. So, so the procedure for Newton's method, so meaning to solve this problem of approximating the solution to f of x equals 0 with some number of steps of Newton's method, is you set C1. So I want to solve. So I want to solve f of x equals 0 for a less than or equal to x less than or equal to b. So step 1 is set C1 equal to any number between a and b. So I chose A. I chose C1 equal A in my iteration, in my Newton's method iteration, but I didn't have to. I could have chosen it to be anything between A and B. And then the second step is you compute C2 as C1 minus F of C1 divided by F prime of C1. So you calculate C2. So you calculate this. Then the next step is you set C3 equal to C2 minus F of C2 divided by F prime of C2. You calculate that. And then you keep going until you get to K, where K is the number of steps that you're asked to do. So, so you say CK is equal to CK minus 1 minus F of CK minus 1 divided by F prime of CK minus 1. And at some point in this procedure, the derivative might not be well defined, in which case your iteration could fail. But in that case, if that happened, so if step 2 fails for some CK, then you could just take note of that. And you don't have to keep going. You generally probably won't be asked to keep going with the iteration. Okay, anyway, so that's basically the procedure for Newton's method. So so I want to approximate this thing, f of x equals 0, for x in a particular range. And the way that I do it is I just produce one of these sequences that I was describing in this boxed, this boxed area. And yeah, doing it is pretty easy because basically I'm giving you a formula for how to compute the next element in the sequence given the element of the sequence that you're at. So, and as long as that, this formula is well defined, so the derivative in particular is not 0, then you're golden and you can just keep computing things until you're done computing some number of steps. Okay, anyway, so does anyone have any questions about Newton's method? I think the only place where you're going to have to do this in the homework is in like the optional exercises, so it won't come up in the directly.
Is it going to be on our test?
Oh, sorry, hold on. Go ahead.
Is this only going to?
Why can't I hear you?
Material?
This is like not good. Huh.
Hello.
Okay, Sarah, do you mind if you're speaking? Do you mind like typing your thing? This is like the apocalypse of technical issues here. Thank you. All right, go ahead. I'm reading the chat, so. Oh, okay. So the question is, will it be on the test? It's a very reasonable question. So I think that Newton's method is in the list of topics that. Hold on. I'll answer your question in a second, Michelle. But just to address Sarah's question first. So I believe Newton's method is in the list of topics that are not required for people taking the class pass no pass or pass whatever. So let me check that really quick just to make absolutely sure. But I'm pretty sure that it won't be required as long as you're taking the class pass no pass. If you're taking the class for a letter grade, then I think it will be on the test. Yeah, let me check really quick. Okay. Anyway, so all right. So sorry. Okay, yeah. So Michelle's asking me to just have better handwriting, which I think is acceptable. Yeah, sorry. I'm gonna look up the answer to your question in a second, Sarah, just to make sure that I completed the answer. But anyway, okay. So for Michelle's question, okay. So if step 2 fails, so let me just write this again. Okay. So what I was saying before is if step 2 fails, then Newton's method. Let me say it this way. So if step 2 fails, then you can either start again with a different C1, or state or I guess state that Newton iteration or Newton's method fails. It's possible for Newton's method to just not work. That is actually a completely possible scenario. But generally speaking, what you probably, a lot of the time when step 2 fails, what actually happened is you picked a bad C1 and you ended up just pushing you onto a point where the derivative vanishes. But I think in general, you can expect this step 3 not to happen. So in general, if you're asked to use Newton's method to compute something, I think that we will not give you a function where it will fail, but where you'll have a situation where the derivative vanishes like that. Yeah, so let's just assume that it's a non-issue. Yeah. Okay. So that's it for today. I'm going to look up this thing about whether or not this Newton's method will be on the final really quick. So you're free to stick around for me to answer that question. As you guys are free to go. And yeah, I'll post this video to the YouTube channel. So yeah, stuff will be available. Okay. Yeah. So okay. So yeah. So Sarah, the announcement that Wilkening made that was titled "Please read Midterm 2 Logistics and Modified Syllabus." That in that announcement he said Newton's method will now be required only for students taking the course for a letter grade. So you only need to know this for the final if you were taking the class for letter grade. Yep. All right. See you guys. We'll start at 510, just so you know. All right, hey everybody. All right, we're gonna get started. So, yeah, all right. Let me just get the pen ready, everything. All right, so some quick announcements. So first of all, I have this YouTube playlist that with recordings of the section. I can give you guys the link now. But yeah, I mean, soon all of the stuff that all of these videos that I'm making, like the just recordings of these sections will be posted there. This section is being recorded just to let you know. And I think this should be the playlist link. So let me just send it to you really quick on the chat. Okay, so I just sent the link to the channel right there. All right, and this section will be posted once everything finishes, once it finishes like compiling and stuff. So that usually takes a while, but it should be done by tomorrow. All right, so the other thing I wanted to say was that midterm grading is almost done. So the students who come to section regularly seem to have done pretty well, so that's great. And yeah, and otherwise, hopefully we'll be done by tomorrow. But basically just the submission complexities for this particular, for the way that we ended up doing everything, made grading a little slower than usual. So we're not quite done yet. But we should be done soon. Okay, so are there any logistical questions about anything before I get started with the actual material?
Oh, I was just wondering if there was like any curve of any sort for the midterm.
Good question. The curve is looking, the curve for this midterm is like kind of, like I can draw it for you if you want what it is right now. There, it looks like this. Kind of. Maybe more like this. Like here, let me just. Okay, so the current curve looks kind of like this, or yeah, something like that. So there's a few people who have gotten perfect scores so far, but and mostly I would say everything is clumped at like near like 14 or 15 or something like that out of a total graded score currently of 18. So yeah, so basically it's looking like the curve is going to be a little bit skewed, but everything should end up being curved in the end. So yeah, there will probably still be some sort of curve, but that's given the grading distribution currently, it seems like a lot of people are getting relatively high scores. So hopefully that doesn't throw the curve off too much.
Okay, sounds good. Thank you.
Yeah, no problem. Okay, so all right, so now let's get started with the main material. All right, so the first thing I'm going to talk about today is L'Hopital's rule. So here, all right, so what does L'Hopital's rule say? So I want to evaluate a limit of the form, of this form, right? So limit of f of x over g of x as x goes to some constant a. And the situation that I'm in is a situation where the top and the bottom are not well defined at a. So the usual situation where this happens is if both f of a and g of a are 0. So if f of x and g of x are continuous, then as I take this limit as x goes to a, both the top and the bottom go to 0. So I get kind of a 0 over 0 situation. And the ratio, so the limit is not really like clearly well defined in any way. Like I can't just evaluate f and g at a and take what the value is, right? So okay, so L'Hopital's rule tells you something you can try to do in this situation. And the simplified version of L'Hopital's rule is this. So let's say I have f of x and g of x. They satisfy this first this condition 1 that I wrote right here. And let's also assume that f prime of a and g prime of a are finite and non-zero. Then in that situation, the limit as x goes to a of f of x divided by g of x is equal to the limit as x goes to a of f prime of x over g prime of x. So basically, I can take the limit that I can take the previous fraction that I was taking the limit of and replace the top and the bottom with their respective derivatives. And in that situation, and then because of the hypotheses that f prime of a and g prime of a are finite and non-zero, that limit is just going to be equal to f prime of a divided by g prime of a. So this makes it really simple, really straightforward to evaluate limits like this, which is pretty cool. All right, so here's an example of L'Hopital in action. So I want to find the following limit using L'Hopital. The limit is x goes to 0 of e to the x minus 1 divided by 2. Right, so here, okay, so first we should check that L'Hopital actually applies in this situation. So if I look at f of x, well, f of x is 0 at x equals 0 because e to the x is 1 and e to the x, so e to the 0 minus 1 is 1 or 0. And then g of x is 2x, sorry, it should say 2x. Change that. Yeah, so g of x is 2x. So in particular, g of x is also 0 at 0. Okay, so then the derivatives are given by f prime of x equals e to the x and g prime of x equals 2. So then I can use L'Hopital to say that the limit is x goes to 0 of e to the x minus 1 over 2 to the x, 2x, which is the limit I want. Should also say that. Sorry about all the typos. So e to the x minus 1 over 2 times x is equal to the limit is x goes to 0 of e to the x over 2, which is 1/2, right? So hopefully that made sense given the typos. It's very difficult to get these all squared away. Okay, anyway, so yeah, so that was the example that I wanted to do L'Hopital for. So e to the x minus 1 over 2x, and that's how it works. All right, and so now, yeah, so there's a more general version of L'Hopital that applies in situations where f of x and g of x go to infinity. So this is the general, so the previous version only applied when, the previous version was just stated for f of a and g of a equals 0. But another situation I can have is the following. So let's say I have f of x and g of x, and they satisfy one of the following two conditions. So either the limit as x goes to a of f of x is 0, and the limit as x goes to a of g of x is also 0. So basically that's the situation we had in the simplified version of L'Hopital. Or I'm also going to allow the situation where the limit as x goes to a of f of x is plus or minus infinity, and the limit as g of x goes to a is plus or minus infinity. So in that case, instead of both the top and the bottom of the fraction going to infinity, instead of the top and the bottom of the fraction in f of x over g of x going to, both of them going to 0. In number 2, you have both of them going to infinity. So we have like an infinity over infinity type situation. Okay, so if either of those two cases holds, then the limit of, the limit of f of x over g of x, so the limit of this thing we want to evaluate, is can be calculated as follows. So if the ratio of the derivatives, so f prime of x over g prime of x, goes to some constant as x goes to a, then the limit as x goes to a of f of x over g of x is going to also be c. So that means that in the case where the ratio of the derivatives goes to some constant, then I can replace the original ratio with the ratio of the derivatives and then take the limit. So basically that case is the same as before. That's exactly what I was saying in the simplified version of L'Hopital. And then so in the second situation that I have is if f prime of x and g prime of x actually diverge. So it's possible for f prime of x and g prime of x to go to plus or minus infinity. And in that case, that f of x and g of x over g of x will also diverge to plus or minus infinity. So basically, even in the cases where f prime of x and g prime of x have a well-defined limit as plus or minus infinity, so that means that, as x goes to a, those things go to infinity or negative infinity, one or the other, then I can also use that to deduce something about f of x over g of x diverging. All right, so let's do an example. So here's an example of the more complicated version of L'Hopital. So here in both situations, I'm going to have ratio of functions that are going to infinity. All right, so the first example is e to the x minus 1 divided by 2x minus 2. So here, if we use L'Hopital's rule, first of all, this is the situation where as x goes to infinity, e to the x minus 1 and 2x minus 2 both go to infinity. So here, if I take the derivative, if I take the derivative of the top and the bottom, I get e to the x over 2. Now the bottom one is constant, so that one doesn't go to infinity as x goes to infinity. But the top one now still goes to infinity. So the limit of this is infinity. It's just plus infinity, because as I take x very large, this thing, e to the x gets very large. So in particular, the limit doesn't exist, so this diverges. This diverges, and it diverges to infinity, so it diverges to plus infinity. All right, so that's that example. All right, for the other example, we can try again to apply L'Hopital. So here we're again in a situation where as x goes to infinity, ln of x squared and x both go to infinity. So we have the infinity over infinity case of L'Hopital. And here, if I take if I look at the limit as x goes to infinity of ln of x squared divided by x, and I take the derivative, I get of both of the top and the bottom, I get 2 ln of x divided by 1, which I can rewrite as 2 ln of x over x. So this is the limit that I get by applying L'Hopital. And here I'm again in a situation where as x goes to infinity, the top and the bottom both go to infinity. So what I should do here is I should apply L'Hopital for a second time. So now I should apply L'Hopital to this guy after, which I got by applying L'Hopital once already. If I apply L'Hopital to this, I differentiate the top and the bottom. I get 2 over x divided by 1. And the limit of that as x goes to infinity is clearly 0, because that's equal to 2 divided by x. And clearly 2 divided by x goes to 0 as x goes to infinity. So so these are two examples of L'Hopital in action in this more general incarnation. Okay, so are there any questions about any of this L'Hopital stuff? So any of this, either the simple version or the general version, or any of the examples that I did? Okay, it looks like no. So if there are no questions, then why don't you guys give these exercises a shot? So here you're being asked to evaluate the following limits, and I'm also going to edit this and say you should evaluate the following limits, or state that the limit diverges. So it's possible that the limit will diverge. Okay, and I'll give you guys until 5:30, I'll give you 10 minutes, so 5:33 to give these a shot. So yeah, and of course feel free to ask me questions while you're trying these out. And I think you should try to ask me the questions on chat, because I think the mic is not working very well. So, or my headphones are kind of malfunctioning a bit. All right. Anyway, so yeah, I'm giving you until 5:33 to give these a try. All right, let's go over these exercises. So let me get the pen ready. All right, so for A, all right, so for A is the one that's the most straightforward. So here, okay, so x over x times e to the negative x goes to 0 as x goes to 0, and so does 2 over e to the negative x minus 2. So here the limit as x goes to 0 of this thing by L'Hopital is equal to the limit of the derivative of the top and the bottom. So we can compute that divided by negative 2 e to the negative x. So the limit of this as x goes to 0. Right, and that limit is sorry, I got to move some windows here. All right, and that limit is okay. So if I now both of these are just well defined at 0. So the top and the bottom both just have values at 0. So the limit is just the ratio of those values. So I have on the top e to the negative 0 minus 0 times e to the negative 0, so that goes away. And then the bottom I get negative 2 e to the negative 0. So the result is 1/2, which is pretty simple. All right, so for B, if I look at the limit as x goes to 0, all right, so I'm looking at this limit.
Oh, wait,
Yeah.
for part A, is it negative 1/2 because the bottom?
Oh, sorry. Yep. Thank you.
Cool.
Thanks. I love it when you catch my mistakes. It means you're paying attention. That's great. Okay, so thank you. All right, so e to the negative, yeah, so it's negative 1/2. All right, so now, all right, so for B, I have limit of as x goes to 0 of ln of e to the x plus 1 divided by 2 e to the negative x minus 2. So just like before, this bottom guy is going to 0, but now the top guy has a value at x equals 0, right? This guy is just ln of 2 at x equals 0, and ln of 2 isn't 0. So this actually diverges, because basically this is some constant, non-zero constant, divided by something going to 0. So that means the resulting limit is infinity. So this one actually diverges. All right, and then for C, and feel free to interrupt if you had questions about B, but for C, if I look at this limit, okay, so e to the x squared minus 1 over x squared minus 1 over x. Okay, so here, each of these fractions individually diverges. So, but when they're combined, they converge. So here I have to combine these to one fraction and then evaluate the limit like that. So if I do that, well, I can write this as limit as x goes to 0 of e to the x minus 1 minus x divided by x squared. This just comes from taking the 1 over x and multiplying it by x over x, and then combining all of the things into one fraction over x squared. Okay, now I apply L'Hopital once. I'm just going to write that as equal L comma L parentheses H. So if I apply L'Hopital once, that says that this limit is equal to the limit of e to the x minus 1 divided by 2x, right? So that's one application of L'Hopital. And then here, because both of these are because the limits are 0 over 0 in this situation, I have to apply L'Hopital again. So if I do it again, I get e to the x divided by 2, which is just 1/2. So all the limits I chose today ended up being 1/2, which is kind of boring, but yeah. So this one ends up being 1/2, and I believe that time I got the sign right, so that's good. All right, so that's how you solve those three. Are there any questions about that before we move on?
Yeah, I have a question about B. So like, do you just have to like recognize like because of like the top and bottom like that like those type it just like diverges?
Well, because you just have to recognize that the top converges to something finite, right? The top converges to something, like the top converges to some number, right?
Mm-hmm.
But the bottom converges to 0.
Okay.
right? So that means that if so it converges to something, like what it does is it converges to like a constant, basically a constant times the limit of the limit of 1 over the bottom, which is going to be infinity. So yeah, I mean, basically this is just kind of another problem. It's recognizing here, the point is you recognize that L'Hopital doesn't apply, and then you just use normal reasoning about limits. Because basically when either the top or the bottom converges to something finite, then you actually should be able to figure out what the limit is based on what the other thing converges to.
Okay.
Does that make sense?
Yeah, kind of. Okay,
Okay.
sounds good.
Yeah. So basically, this is just a situation where L'Hopital isn't useful.
Okay.
Mhm.
Thank you.
No problem.
So L'Hopital is basically used when your limit after you plug in, like the x equals or x goes to 0, it's either 0 over 0 or infinity over infinity. Is that
Yeah.
correct?
Yeah, or plus infinity, like it could be minus infinity over minus infinity, but
Okay.
the point is that if the limit of the top and the bottom go to either 0 or infinity,
Mm-hmm.
like both at the same time, so they either both have to go to 0 or both have to go to infinity, then you can apply L'Hopital.
Okay, so basically, if the top and the bottom are equal to each other, so 0 or positive infinity or minus infinity, then you would use L'Hopital.
Yeah, but if they're just equal to each other, like, and they're just numbers, like they're both the limits are 5,
Yeah.
then the limit would just be 1.
Okay, yeah, that makes sense.
Yeah. So it gets more, basically when they both go to infinity or 0, that's when it gets a little subtle.
Okay, sounds
Yeah.
good. Thank you.
No problem. Okay, so all right, so now we're going to move on to the second thing for today, which is indefinite integrals. All right, so sorry, this window's a little messed up. I've been having a lot of tech trouble today. It's been a bad tech day. Are you gonna do something here? Give me a moment. Okay. All right. Anyway. All right. So what's an indefinite integral? So an indefinite integral is an integral where the bounds of integration are infinity or negative infinity or something like that. So more precisely, okay, so here's the first example of type of indefinite integral. So if I write the integral from, so let's say I have a function f which has an antiderivative big F. So that means big F is the integral of little f up to some constant. Then I can define the integral of f from a to infinity. So that's this integral. I can define that integral as the limit as b goes to as this is a definition of that integral. I can define it as the limit as b goes to infinity of the integral from a to b, so from a to b, of f of x dx. Or equivalently, this is the same, literally writing the same thing once you evaluate this integral from a to b, as the limit as b goes to infinity of big F of b minus big F of a. So basically, the way that I define the integral from a to infinity is I take a finite integral, so an integral from a to some finite b, and then I take the limit of that integral as b gets arbitrarily large, so as b goes to infinity. Okay, and then the limit on the left, if the limit so if this limit exists, then I say that the integral converges. If the limit doesn't exist, then I say that the integral diverges. So basically the integral either converges when that limit exists and then it just gives you a number, or it diverges and you get nothing. You get not a well-defined integral. Okay, so that's that kind of indefinite integral. And I can similarly define the integral from negative infinity to b for some finite b, and the integral from negative infinity to positive infinity by doing the same thing. So basically all I do is I take the, for this one, I would take the integral from a to b, and then I would take the limit as a goes to negative infinity. For this one, I would take the integral from a to b, and then I would take the limit as both b goes to infinity and a goes to negative infinity. Okay, so now that's like the general definition of these indefinite integrals. So now let me do an example. All right, so here's an example of a kind of question you could be asked. It's find the following indefinite integrals. So the first one is integral from 2 to infinity of 1 over x squared. The second one is integral from negative infinity to 0 of e to the x. All right, so the way you do this is you literally just use the definition and then use your normal integration prowess to do this. So if I write integral from 2 to infinity of 1 over x squared, this is by definition the limit as b goes to infinity of integral from 2 to b of 1 over x squared. Now, the integral of 1 over x squared, the antiderivative of that is just negative 1 over x, right? So this limit, so this integral can also be written as negative 1 over b minus negative 1/2. So this is just evaluating this inner integral. And now I just take the limit of this boxed thing as b goes to infinity. And so as b goes to infinity, this negative 1 over 1/2 part doesn't depend on b. So that just that stays the same. But the negative 1 over b part goes to 0 because as b goes to infinity, that part just vanishes, right? So the resulting integral is 1/2. Okay, and then I have a similar kind of thing for the integral of e to the x from negative infinity to 0. So here I look at the limit as b goes to negative infinity of the integral from b to 0 of e to the x, right? So the integral of, the antiderivative of e to the x is just e to the x plus c. So when I evaluate this integral and do the usual thing with the bounds, I get e to the 0, which is 1, minus e to the b, which is minus e to the b. And now if I take the limit as b goes to negative infinity, that should say negative infinity. So let me fix that. Yeah, so I take this limit as b goes to negative infinity, the e to the b part will go away because e to the as b goes to negative infinity, e to the b gets very, very small. So the limit there is just 1. So that's 1. Okay, so those are the two examples. So before I give you guys the exercises, do you guys have any questions about how to do this? It's not super complicated, I think.
So,
Sorry, say it again.
so it's basically just like it's almost like taking the limit out, right, of the integral and just substituting with the variable. That's
basically that's kind of the idea. Yeah, that's basically the idea. It's like that's exactly the idea. Is that you just take, instead of writing it as a limit as b goes to infinity of this integral from a to b, you just replace the b with an infinity.
Okay.
And then it's just notation. This indefinite integrals are just notation for that.
Gotcha. Yeah. Okay. Thank
you. Yeah, and they're basically not harder to evaluate than normal integrals. That's kind of the point, is they're the same. You just have to know how to do normal integrals, and you need to know how to take limits. So, yeah. All right, so now I'll let you guys try these exercises. Okay, so it's just compute these two integrals, these two indefinite integrals. And I will give you guys, I'll give you guys like 10 minutes, so I'll give you until 5:56. And I'm going to mute myself so I don't interrupt anything. And yeah, feel free to speak up or to message me on the chat if you have questions. All right, let's get started with the solutions. Okay, so for the first one, let me call this one A and this one B. Okay, so for the first one, all right, so I'm taking this integral 3 over x cubed dx. It's terrible. Cubed, whatever. All right. So, okay, so this thing is equal to, by definition, the limit as x goes to infinity, or sorry, I should say b goes to infinity. Yikes. All right. So it's the limit as b goes to infinity of the integral from 2 to b of 3 over x cubed dx. Okay, so 3 over x cubed is the derivative of negative 3 over 2 x to the negative 2, right? So this I can write as the limit as b goes to infinity of negative 3 over 2 x to the negative 2 with 2 and b plugged in. So that's, sorry, I'm running out of room here a little bit on the window. Stop it. Give me a moment. Okay, yeah, so that's this, so that's that. And now I can write that as the limit as b goes to infinity of negative 3 over 2, and then I just plug in b, so I get b to the negative 2 minus 2 to the negative 2. And now as b goes to infinity, this b to the negative 2 part goes to 0. So the resulting limit is just 3 over 8. So that's the answer. All right. So then the second thing is, so okay, so now going on to b. All right, so this one's a little scarier looking, but it's not so bad. So for an integral like this, I'm supposed to write a double limit. So now I have to take the limit as b goes to infinity and a goes to negative infinity of the integral from a to b of 2x divided by 1 plus x squared dx. All right, so now to do the inner integral, to do this, sorry, I'm trying to move a window here. All right, so to do the integral from a to b of this thing, you can either do u substitution or you can observe that, so 2x to the 1 plus x squared to the negative 2 is just equal to the derivative of 1 plus x squared to the negative 1 negative, okay? So this fact means that I can write this limit as, okay, limit as a goes to negative infinity, b goes to infinity of this thing right here, negative 1 plus x squared to the negative 1, evaluated at a and b. Okay, now I just need to look at each of these individual pieces. So, all right, so I can write that as, maybe I'll write it one more time just to totally expand it out. So I can write that limit now as limit as a goes to negative infinity, b goes to infinity of 1 divided by 1 plus, so negative 1 divided by 1 plus a squared, or sorry, b squared. Move this a little bit. There we go. Okay, so negative 1 divided by 1 plus b squared minus negative 1 divided by 1 plus a squared. Okay, so that's the whole thing. Now, as I take a and b going to infinity, both of these terms go to 0, right? So if I take the limit as a goes to infinity, the a term goes to 0. If I take the limit as a goes to negative infinity. And likewise, if I take the limit as b goes to infinity, I get negative 1 over b squared. That thing also goes to 0. So both of these terms go to 0 as as a and b go to infinity. So the limit is going to just be 0. Yeah, so the only tricky thing here is kind of wrapping your head around the double limit, and otherwise the thing pretty much pops out pretty easily. So the integral ends up just vanishing completely. Okay, so are there any questions about either of these two integrals?
I was just wondering for part B, will we be required to show like our work like limit b goes to infinity and a goes to negative infinity? Because I just wrote like the first part, like the integral of infinity and negative infinity, and I directly jumped to like the last part, but without like the limit, like writing like the limit stuff.
You just jumped from integral from negative infinity to infinity is just 0?
No, I took like the integral of 2x over 1 plus x squared and that whole thing squared, but
Yeah.
like I didn't write like limit b goes to infinity, a goes to negative infinity. Like I don't know if how it is in like math terms, but like I wrote negative 1 plus x squared and that whole thing to the negative 1, and then like I just have to like take like b is infinity and negative a is negative infinity, but I didn't write
Yeah, I mean, if you wrote something like that, I think that would be fine, because that's kind of using this thing that sorry, a bunch of my papers just fell over. I'll get that in a second. Yeah, so I think so that's like using this antiderivative thing where you're just writing it as like limit as a goes to infinity, b goes to infinity of f of b minus f of a.
Mhm.
I'm not sure if I would use infinity as like an entry necessarily. Like you can't really enter infinity into a function. But I think that, yeah, I mean, I think skipping straight to the step where you're just kind of like, well, I mean, I feel like, yeah, that sounds okay to me. I don't know. It's always safer to show more work, right?
Okay, yeah,
But
okay.
but I think that sounded okay. That what you said sounded fine to me.
Okay, sounds good. Okay, thank you.
Yeah. All right. Any other questions about this stuff before we do the last thing? All right. Okay, so the last thing, it has no the last thing, I'm not giving you guys an exercise with this. This is just, I'm just going to give an overview of this material. So this is material that will not be on the final if you are taking the class pass no pass, but it will be on the final if you're taking it for a letter grade. So if you're taking it for a letter grade, this material is, you need to know this stuff. Okay, so this is about Newton's method. So Newton's method is a method which applies to, so it's similar to Euler's method. It's a method of approximating a zero of some function. So let's say I want to find a solution x to the equation f of x equals 0 for x between a and b, right? So I want to find an x that solves this f of x equals 0 equation, where f is just some function. I don't know what it is yet. For where x is in some specified range of a and b. So it can go from like a is, maybe a is 1 and b is 5. So x is between 1 and 5, but generally it could be anything. All right, so in general, if I give you an arbitrary function, a lot of the time it's very difficult to solve this equation explicitly. Like it's just hard to find a solution exactly, So to find an approximate solution, there's a method called that's what Newton's method is for. So Newton's method starts with the following fact. So let's say I have a function f of x, and let's say I have a sequence Cn that satisfies the following. So that satisfies the following like recursion relations. That means it's, Cn is defined in terms of Cn minus 1 as follows. So the term Cn is given by Cn minus 1 minus f of Cn divided by f prime of Cn minus 1. Sorry, and this should be C sub n minus 1. I made that mistake on the last talk too. All right, so anyway, so the point is that I can define Cn in terms of Cn minus 1 and f and f prime at the value Cn, at the entry Cn minus 1. Okay, so this is just some weird formula for some sequence that I can construct, right? And here I'm assuming that all of this stuff is well defined. So I'm assuming that f prime of Cn is non-zero for any n, and I'm assuming that this sequence has a limit. Then in this situation, the limit is a 0 of f. So basically, if I construct a sequence like this, then the sequence Cn approximates a 0 of f, meaning as n gets larger, Cn gets closer and closer to a 0. Okay, so that's all a little bit abstract, but maybe a step-by-step procedure coming out of this fact is the following. So let's say I want to approximate f of x equals 0. I want to find an x such that f of x is approximately 0 and x is between a and b, right? So I want to find something that approximates a 0. Then I want to, here's a procedure for finding an approximate 0. So finding an approximate x that approximately satisfies this thing. So first, I check that a solution exists between a and b. So usually that means I check that f of a and f of b, this should say, sorry, I should change this to, so I check that there's a solution between a and b, which usually I do by checking that f of a and f of b have different sign. So that means that I'm checking that somewhere between a and b, there is a 0 of f, right? Then step 2 is that I check that the derivative is not 0 anywhere between a and b. That's the second thing I want to check. So if both of those work, then I can set C1 equal to A or any number between A and B. So I'm allowed to pick whatever number I want. It doesn't really make a difference. And then I compute, so then I start with this number C1. So that's the first element of my sequence, C1. And then I compute C2 from C1 just using this formula, right? So that means I'll set C2 equal to C1 minus f of C1 divided by f prime of C1. And then I'll do it again to get C3. So I'll set C3 equal to C2 minus f of C2 divided by f prime of C2. Then I get C4 by doing it again. Then I get C5 by doing it again, et cetera, et cetera, et cetera. And then eventually, when I've reached the desired number of steps, so basically I can do as many steps as I want. And usually in a problem, you'd be told like do 5 steps or do 6 steps. So when I reach the desired number of steps, then the resulting CK that I get is the approximation that I'm looking for. So the CK is the approximate x. So I can take x equal to CK, and that will be an approximate 0. So that's the procedure. So this is actually the method itself. The thing about the red box thing above it is more of a theorem that tells you that the method works. Okay, so let's see what an example looks like of this step-by-step process in practice. Okay, so so I want to approximate a solution to 3x cubed minus x squared plus 5x minus 12 equals 0. So I want to find so f of x is this whole thing, and I want to solve f of x equals 0 for x between 1 and 2. Okay, and I'm told to do 4 steps of Newton's method, so I want to approximate it with 4 steps of Newton's method. All right, so the first thing I should do is I should check that this thing has that I kind of skipped this step in here, but I want to check that there is a solution between 1 and 2. So if I plug in 1, right? So if I plug in 1 to the function, I get 3 times 1 squared minus 1 squared plus 5 minus 12. And that is 3 minus 1 plus 5 minus 12, which is negative, what is that? So that's like negative 5. No, sorry. Wait, so that's 8 minus 13, which is, yeah, that is negative 5. Great. Okay, so that's negative 5. And on the other hand, if I plug in x equals 2, and let me close this window really quick. If I plug in x equals 2, I get 3 times 2 squared minus 2 squared, sorry, 3 times 2 cubed minus 2 squared plus 5 times 2 minus 12. And that's 3 times 8 minus 4 plus 10 minus 12. And you can check it's pretty clear that this is positive, right? Don't even have to add all that up. So together, that means that because this is negative and because f of 1 is negative and f of 2 is positive, that means that by the intermediate value theorem, there has to be a 0 in between 1 and 2. So that's pretty important. So I just checked the first step. I just did step 1, which is I check that there is a solution between A and B. Okay, then the next thing I have to do is I have to check that f prime is not 0 whenever x is between 1 and 2. And there I can just plug it in. So I check that 9 times, I can just kind of eyeball it. So if I look at 9 times x squared minus 2x plus 5, you can see here that if I plug in any number that's between 1 and 2, this will always be positive. So I can't have a 0 in between there. So basically, the derivative never vanishes between 1 and 2, but there's a 0 of f itself in that range. So that verifies 1 and 2. So based on both of those working, now I can find an approximate 0 by following the procedure that was set out here. So I take C1 equal A, so that's C1 equal 1. Then I calculate iteratively 4 elements of this sequence Cn, right? So C2 is given by C1 minus f of C1 divided by f prime of C1. So that's 1 minus negative 5 over 12, which is 1.4167. And don't worry about that stuff. Then I do it again. So I take this value for C2, I plug it into this formula, and I get C3. And when I plug it into that formula, evaluating f and f prime at C2, then I get 1.3373. And then if I do it again, I calculate C4 using C3, and I get 1.33333, whatever. And actually, if you check, so this thing, maybe I'll continue it with zeros. Now C4 is my approximate solution. So that would be, so my answer would be this, right? And you can check that this thing is approximately a solution because this thing, so C4 is approximately equal to 1/3. And lo and behold, if I plug in 1/3 to this polynomial, I plug in 3 to the 1/3 cubed minus 1/3 squared plus 5 times 1/3 minus 12, then I should get, well, maybe I don't. That's not good. This should be a 0. Oh, sorry, it's not 1/3, it's 4/3. That makes more sense. 4/3. Okay, so if I plug in 4/3 to this thing, then I get we can just kind of work it out. So I get, let's see. Now you guys get to see me do. So I get 64 divided by 27 times 3 minus 16 divided by 9. Plus 20 divided by 3 minus 12. And if I simplify that a little bit, I get 64 divided by 9 minus 16 divided by 9 plus 60 divided by 9 minus 80. Wait, no, that's not 21 divided by 9 minus 108 divided by 9. And if I did all of that correctly, so I get 124 minus 124, so the result is 0. So 4/3 is the exact 0, right? And this thing just calculated an approximate version of 1/3. So that's basically that, this process working in action. Okay, so anyway, so that's Newton's method. So that's how it works. So you just apply this step-by-step procedure, and it will spit out an approximate 0. Okay, so do you guys have any questions about this?
I think one question I have is, so when do you kind of know when to stop, I guess, approximating?
So you will either be told to calculate it up to some number of digits, and then once it stops changing up to that number of digits, then you can stop. So
okay,
that's one thing you could be told. Or the other way is they'll just tell you do 5 steps.
Okay, gotcha.
Yeah. So those are two. It should be one of those two things.
Okay.
Yeah. And if it's vague, you can always just ask.
Okay.
Yeah. All right. Any other questions? No? Cool. All right. Well, that's everything. I think you guys, the grades should be out pretty soon. I think you guys both got A's, so good job. Yeah, they'll be out pretty soon. Actually, I think everything's graded, so I can now tell you guys things about the grades. But anyway, so so we can talk about that. I can DM you your score if you want. Otherwise, Otherwise, I'll see you guys next time. Yeah.
Sounds good. So are all the scores graded then? It's just you guys have to put it in?
Yeah, we just have to post everything. We just have to, Wilkening basically just has to post it, but I think actually one grader has to do has to grade like 6 things. So I'm not sure if Wilkening is just going to do that or if they're going to do it, but they should be out pretty soon. Your guys's are graded and the statistics are pretty much set in stone.
Okay.
Yeah. Right. So maybe you guys should probably just wait for your grades, but you guys both did pretty good. So good job.
Okay, cool. Thank you.
No
Thank
problem.
you.
See you next time.
Yep.
All right. Bye.
Take care.
You too.